Here we'll be looking at the equations that are used in the design of a wetland wastewater treatment system. This would be applicable to the case where we're treating organic wastes that for anaerobic conditions, so producing ammonia and nitrate from that process. We're also using the wetland to reduce the nitrate output under anaerobic conditions. So we have waste product, that's waste material which is being discharged in the wetland, breaks down, produces ammonium. That ammonium is oxidized to produce nitrate, and then we use the same system for denitrifying the resulting nitrate. We assume here that the flow is that the wetland behaves as a plug flow reactor, that the flow is steady in the wetland, that the reaction rates are linear, and that there are no limitations to any of the reactions. So in other words, we're saying that there's plenty of bacteria to do the either the aerobic or anaerobic treatment processes, that when necessary there's plenty of oxygen to produce those to produce that treatment process, and also that nutrients are not a limitation either. So first we have the hydraulics of both free water surface wetland and for subsurface wetland. The one possible equation that can be used to calculate the mean velocity in a wetland at any given cross-section of the wetland is Manning's equation, so that the velocity is just proportional to the depth of flow raised to the 2/3 power, and S would be the slope of the wetland, typically a very small value for that slope. In reality, the small s is the slope of the water surface, but here we'll assume that it's the slope of the wetland. N is the roughness factor, which depending on the type of vegetation that's in the wetland, and some values for A are given by Reed in Chapter 6. The maximum length of the wetland is a function of the surface area, the required surface area of the wetland, the discharge, capital Q, entering the wetland, that is the wastewater discharge in the wetland. In here, the factor 86,400 is a conversion from seconds to days, because there's 86,400 seconds in a day. The small m parameter that's in this equation is just the head loss in the wetland, which would be just the difference in essentially though a difference in water surface elevation between the outlet of the wetland and the inlet. And so we would restrict m to some value between 0 and 1. That is, m is a fraction of that, it's expressed as a fraction of the design depth h. So if for instance the value of h, the average depth of flow, is 1 meter, and if I set m to be equal to 0.1, it would mean that the head loss between the outlet and the inlet of the wetland would be 0.1 meter, or 10% of 1. Capital W is the width of the wetland, which is just the area of the wetland that's required to treat the wastewater divided by the length of the wetlands. For subsurface wetland, we have equations that describe the Darcy flux, small q, which is just the discharge divided by the width, product of the width and the depth. This is small q is the specific discharge. Units are meters per day. That is also what we call the Darcy flux, and Darcy flux is just the hydraulic conductivity multiplied by the slope of the wetland. The actual velocity, the pore velocity within the porous matrix composing the subsurface wetland treatment material, is just the small q divided by the porosity of that treatment material, porous treatment material. And the minimum required width of the wetland is given by this formula, where capital Q again is discharge into the wetland. AS is the surface area of the wetland that's required to treat the wastewater to the level that's needed. M is again that fraction of the depth, which represents the allowable head loss in the wetland. And KS is the saturated hydraulic conductivity of the bed material. Okay, we'll show how to calculate AS, which will be a function of a number of parameters, such as, or variables such as the depth of flow and the rate coefficient for degradation of whatever organic material is present. The rate constant for the degradation rate is a function of the water temperature. What we would do here is we would take the temperature of the water entering the wetland and the temperature of the water exiting the wetland at the effluent end, average those two to calculate what we should use for the rate constant. So we do need to know how the temperature varies between the inlet and the outlet of the wetland. This formula is for a free water surface wetland. It allows you to calculate the water temperature at any given point X along the wetland, where X0 is the reference distance associated with the entrance to the wetland. X0 could be 0, generally would be 0, but it could be any number that you want to use as your reference. And X is the distance from that entrance point that you're interested in the temperature of the water. Now, if we want to know the temperature at the effluent point, well, the wetland has a length L between the entrance and the effluent point, then I would substitute L, the length of the wetland, in for the value of X. In the formula, T0 is the water temperature at the entrance, that is from the wastewater treatment plant. TW would be the water temperature at the given point X, and Tair is the air temperature. The coefficient, or the parameter US, U subscript S, is the coefficient heat transfer from the water surface. And there are a number of values that are given in some of the reference materials, but here the value is given for from Reed's chapter 6, one for dense vegetation and one for open water. If you're somewhere in between dense vegetation and just plain old open water, then you could use a number in between those that ranges in between those two values. Rho W is the density of water, H is the depth of flow, V is the mean velocity of flow, and C sub P would be the specific heat of water, which is 4,180 joules per kilogram degrees C of water. Now that's for conditions where you don't have any ice coverage. As soon as you have any ice coverage on a portion of the wetland, that will affect the heat transfer rate. So the next page shows what would be the variation in temperature if you have the lower part of the wetland, the lower end of the wetland, being covered with ice. So at some point you discharge water into the wetland at temperatures well above 0 degrees. As the water moves down the wetland, it gets colder and colder, and eventually you could reach the point where ice would form on the wetland surface. Here the standard is to use the temperature at which the ice freezes to be 3 degrees centigrade. That of course is not exactly correct, because water freezes at 0 degrees centigrade if it's pure water. The value of 3 degrees is used because we're calculating the average water temperature over the entire depth of the flow. And while the surface might be close to 0 degrees, the bottom of the wetland will not be at 0 degrees. So the 3 degrees accounts for the fact that there's a variation in temperature across the depth of the flow. And just based on experience, that number is a value that's been specified to be the temperature at which you'd first start seeing ice form. Here, in this formula, we're calculating the temperature of the water down gradient of the point where ice first forms. And the point at which the ice forms is given here as xi. So it's somewhere down gradient from the entrance of the wetland. That value of xi can be calculated from the previous formula. We could calculate the value of x equal to xi by setting Tw equal to 3 degrees. That is the temperature at which we know that ice will begin to form. And we could calculate what would be the value of x where that water temperature of 3 degrees would be reached within the wetland. Using that value of xi, we can then substitute into this equation and calculate the water temperature down gradient of where ice first forms. The heat transfer coefficient is a bit different than the one that we just used for the previous open water surface or ice-free surface case, because now we have to account for the fact that the surface is covered with ice. And the formula for calculating UI is given here on the page. The value of the parameters, or the T0 now, would be the water temperature right at the beginning of the ice-covered section. Tm would be the melting point of ice, or 0 degrees, and Tw would be the temperature downstream of that. So if we had used 3 degrees as being our temperature at which ice first starts to form in the wetland, T0 would be that value of 3 degrees. This slide shows the formula for calculating the rate of ice formation. We would use this in the case where we're interested in knowing whether the ice, basically that the wetland will freeze all the way from the surface down to the bottom of the wetland, in which case the wetland would fail to operate. We will not be using this in at least the assignment 2. We might do some calculations with this formula later. But if the cold conditions persisted for a long enough period of time, there's a chance that the system would end up in failure, because the ice could thicken to the point where it would actually close off the flow in the wetland. As I say, we'll come back to this equation again if we need to use it. For subsurface wetland, there are 2 formulas given here for calculating the effluent water temperature. And the first equation is 6.22 from Reed, and it's not quite accurate because it doesn't take into account the fact that the heat flux from the wetland actually varies as you go from the upper end of the wetland to the lower end. This here assumes that that heat flux is constant, irregardless of location along the wetland. So the second equation is more sensible, or makes more sense, and I suggest it as an alternative to equation 6.22, because it does account for the fact that the effluent temperature, or that the heat loss from the wetland will decrease as you go from the entrance to the wetland to the lower end of the wetland. In this formula, TR is the residence time in the wetland for the water to move from the upper end of the wetland to the lower end of the wetland. So T0 again is the water temperature of the entrance, T sub E is the water temperature of the exit, and TR is the air temperature. The heat transfer coefficient here is calculated using taking into account all the different layers of material composing the subsurface wetland. You've got the treatment layer, which is a gravel pack that might be, let's say, 0.5 to 1 meter thick, and then you'd have a some other kind of a dry pea gravel pack on top of that, maybe 10 centimeters thick, could be. And on top of that, you might have decaying organic material from the vegetation that exists in the wetland. And then you may even have snow on top of that during the wintertime, which would also provide some insulation. So the value of U is the effective heat conduction coefficient for that laminated layer of different materials. The treatment layer, the pea gravel pack on top of the treatment layer, that's a dry material on top of the treatment layer, and then we have the decaying vegetation and possibly snow on top of that. Each of the thermal conductivities for each of those different layers and the thickness of the layers have to be taken into account. And the thermal conductivity, a table of thermal conductivities for different materials is given in Reed Chapter 6. All right, so we can calculate the temperature of the effluent. As I say, you would take the temperature of the effluent, add it to the temperature of the influent, average those two values, divide the sum by 2, and that would be the temperature that you use for calculating the linear rate coefficient. All right, so we find that linear rate coefficient in this slide. First, we'll look at the equation for DOD reduction. This is assuming a linear rate of degradation, that is a linear variation of rate of degradation as a function of concentration of the waste, organic waste material. That has been taken into account in calculating then the surface area required for the wetland. Here capital Q is the discharge into the wetland, C0 is the influent concentration of the organic waste, C sub E is the effluent concentration. Here K sub T is the rate, the linear rate coefficient, H is the depth of flow specified, and the epsilon is the porosity of the wetland. We can correct the value of the rate coefficient, which is specified here at 20 degrees C at 0.678 per day. We can correct for the actual temperature of the water by substituting in the average of the influent temperature and the effluent temperature for the value of T. And doing that, we would then, of course, have a higher rate coefficient if the temperature is above 20 degrees C and a lower rate coefficient if it's below 20 degrees C. The reaction products from the degradation of the organic waste is given in the bottom of the page, where we see that with oxygen we get CO2, we get water, and we get ammonium or ammonia, depending on what the pH of the system is. BOD reduction for the subsurface wetland, the formula is very similar, but here we see that the rate coefficient at 20 degrees is almost twice the value of the rate coefficient for the free water surface wetland. Just go back here and see that it's 0.678 for the free water surface wetland. It's 1.1 for subsurface wetland. The reaction products are the same, essentially the same as what we saw for the free water surface wetland. Just some examples of performance of some wetlands. Here, percent BOD reduction. This is from the book by Reed, figure 6.12, that shows that you get quite a bit of variation in the performance of different wetlands. And the solid line that's shown here is just basically the plot of the predicted degradation of the organic waste, assuming this linear degradation process, where by linear I mean that the rate is linearly proportional to the concentration of the waste. For a subsurface wetland, we see that the process is a bit more efficient, takes less time. On both of these graphs, the horizontal axis has got the hydraulic residence time, which is just basically how long the waste is present in the wetland. So of course, the longer the hydraulic residence time, the more complete removal of the waste will occur. For nitrogen removal, the BOD degradation leads to ammonia production. The ammonia then ammonia and ammonium. The ammonia is converted to nitrite and nitrate as a result of the nitrification process through oxygen and bacterial action. So both ammonia and nitrate are constituents of concern. There's a nitrate water quality standard of 10 milligram per liter for drinking water. For ammonia, it can be toxic to aquatic organisms at a high enough concentration. and ammonium, which is produced through nitrification of, or through the degradation of the organic waste. They can convert back and forth with ammonia form of that form of nitrogen, and it's all dependent on what the pH of the solution happens to be. But the ammonia can be, which is the unionized form of ammonia, this can be toxic to aquatic organisms. Nitrification or nitrogen transformation processes that are going on in the wetland. Free water surface wetland, you could also think of this as being what you'd see for a subsurface wetland as well. It's just you'd have a porous treatment layer. You have the organics leading to ammonia formation. The ammonia then is nitrified to produce nitrite and nitrate, and then through an anaerobic process, the nitrate will be denitrified to produce either nitrogen gas or nitrous oxide, N2O, which is a known greenhouse gas. So N2O is a bad product to come out of these systems. If the ammonium can also convert to ammonia, which can volatilize into the atmosphere above the water surface. So this illustrates some of the fates of nitrate. It can be taken up by the plant, can be taken up by sediment, a number of different processes that occur here that affect the presence of nitrogen in the wetland. The nitrification process, we have to design the size of the wetland to handle this as well. Same type of formula that we use for the organic degradation. That is, we calculate a surface area for the wetland. The difference here is the value of K sub T is given by a different set of formulas. Again, we have a correction factor for temperature, and you can use these numbers or these equations and expressions here for doing that calculation of what the value of K sub T is, depending on what your average temperature is between the influent and effluent point of the wetland. We'll talk a bit more about nitrification filter bed. There's a note at the bottom of the slide that talks about nitrification filter bed, and I'll skip that for right now. We'll talk about that a little bit later. So what we'd like, of course, would be that for the organics to be broken down to ammonia, and then that will be completely nitrified by the time it reaches the end of the wetland. But in many cases, that won't be the situation, especially if oxygen becomes low within the wetland. It may not be possible to completely nitrify all of the ammonia that's present in the wetland, in which case we need to then use something like a nitrification filter bed to enhance the nitrification process to convert the ammonia to nitrate. Okay, so this for free water surface wetland, we'd get a value of A sub S for the surface area that's required. In many cases, this value of the surface area might be larger than what's required for the organic waste treatment, in which case we have to decide, well, how are we going to deal with that? You'd have to use the larger of those two sizes, whichever one happens to be larger. For the subsurface wetland, similar set of formulas. Here the rate coefficient is calculated, starts off with the calculation of KNH, which is a function of the fraction of the treatment layer that's got roots in it. So if the roots go all the way to the bottom of the treatment layer, the value of RZ will be equal to 1. We use that value of KNH in the formulas that are shown above that. And again, we have a correction factor for temperature. And the same problem with complete nitrification of the ammonia is a problem here for the subsurface wetland as well. So the process is, first we size the wetland for BOD removal. That is, we calculate A sub S that's required for BOD removal, and then we size it for ammonia removal. The larger of the two is used in the design. If generally the size required for ammonia removal or reduction will lead to a larger wetland area than the BOD reduction. And in that case, we might choose to use the nitrification filter bed to keep the size of the wetland smaller. We do not then require the full size that would be calculated for ammonia reduction or ammonia transformation to nitrate. We can eliminate that step by using a nitrification filter bed. So here's just a conceptual drawing of a nitrification filter bed. You've got both a subsurface wetland and a free water surface wetland. At the lower end of the wetland, we've got a pipe that collects the treated water. Presumably at the point where you reach that pipe on the right-hand side, the organic waste will have been converted or treated to the level required, but maybe the ammonia still is at too high of a level simply because there is not enough oxygen to nitrify all of the ammonia. So now we take that water that's got too high of ammonia in it and we pump it back to the upper to the head of the wetland, and we spray that water onto a nitrification filter bed, which is shown on the left-hand side, and water percolates down through that filter bed, and the ammonium in that water is then nitrified, becomes nitrate, and that nitrate-laden water is pumped back into the wetland. And because there's high organics in the flow of the wetland coming from the wastewater, that carbon source from the organics serves to, in the process, anaerobic process of breaking down the nitrate to produce nitrogen gas. The sizing of the nitrification filter bed is given here, where A sub V is the specific surface area of the bed material that's in the filter bed that's required to reduce the ammonium down to allowable exit or effluent concentration, C sub E NH4. The rate coefficient is given there, which is temperature dependent, and K sub T is dimensionless here. The specific surface area is expressed in meters squared per kilogram of ammonium per day that needs to be removed. And so if we know how much ammonium in kilograms is being produced per day by the wastewater treatment system, which we'd know, because if we know the concentration in the ammonium, we know the discharge rate, we know how many kilograms of ammonium are being produced per day, we'd be able to calculate from that what the total surface area is required for treatment of the ammonium. And there's a table in READ which expresses the surface area that's present in each cubic meter of certain types of porous materials, gravel, pea gravel, other types of artificial porous media that can be used to determine what volume of porous media is necessary. So the porous material characteristic would be expressed in specific surface area per cubic meter of the material, and you'd be able to determine how many cubic meters of the material you'd need to come up with the proper level of treatment. The denitrification process, that is, you're going to produce nitrate as a result of the nitrification. is again calculated the same way. The area of the wetland that's required both of free water surface wetland and for the subsurface wetland. We calculate the surface area of the wetland again using a linear rate coefficient, which is temperature dependent, and so we can calculate that. Again, this area is going to be, that's calculated from this, has to be taken into account in deciding which size of wetland we're going to actually design. If this value is much, much larger than the size of either the BOD reduction or the ammonia reduction, then we need to use that larger value to get the appropriate amount of nitrate reduction. Just to show the chemical transformations that occur for denitrification, you've got an organic source or a carbon source in the form of organics that are present in both the free water surface wetland and subsurface wetland. You're taking that and combining it with the nitrate with anaerobic bacteria to produce nitrogen gas, CO2, some ammonium, which does have to be treated as well or taken into account, water, and the phosphorus compound. So that has to be, that ammonium that produced in this process does have to be taken into account. Essentially what happens here is that the nitrate is serving as an electron acceptor rather than what would be normally an aerobic condition, oxygen, to break down the organic material. Just to show what would happen in a conventional wastewater treatment system to remove nitrate, you can either use methanol or glucose as the carbon source, or would be used as the carbon source. Okay, I'm going to stop there. We'll take a break, and we'll continue then after this.